Okay, so let's move on. These are my disclosures. The Daily Mail is not on there, thank God, but we'll move on. So it's a truly remarkable time for haemophilia care, and I think that's been obvious from some of the presentations you've already heard in the last couple of days. This is a slide that comes from a meeting that some of us were at in Washington last October. And you can see that this is the 25th anniversary of a meeting that occurs about every 2 or 3 years, discussing novel therapies for haemophilia. And what's astonishing here, of course, is that there were 42 presentations given in just over a day and a half. So this was, to use Agnes's term from this morning, a tsunami of information about all the new things that are happening preclinically and clinically in the haemophilia field. And this is a rare disease, but it's an expensive disease to treat, as illustrated here. So the global market value for haemophilia therapy is somewhere in this region here, so about $7.4 billion, 0.4 billion pounds per year. And I think there are still some industry folks sitting at the back here. So there's a lot of interest in translating the information that you're going to hear about in the next little while into the clinic, and companies making money. Now, this is also illustrated by this slide here, because I think haemophilia therapy is successful, and part of that is now about haemophilia therapy being big business. And honestly, the new information about haemophilia is not in the New England Journal Blood or Nature Medicine. It's now in the New York Times, Endpoints News, or this week, JP Morgan conferences. So honestly, you have to keep up by looking at things which are not the conventional medical peer-reviewed articles, but they're in these news releases. This honestly makes me a little nervous, but I think it's the reality of the success of the field that shareholders in the companies are extremely interested, and the companies will release good news early because they want this to be good for their companies. You see at the bottom here that these were ASH abstract drops. So the losers are piling up. So the companies are looking at the abstracts now, and their shares are going up or down based upon abstract submissions. It's an interesting world we're living in. So here's what I'm going to talk about. I'm very briefly going to discuss some issues about some of the other forms of therapy, and then obviously going to spend most of my time talking about gene and cell therapies for haemophilia. So here are some of the novel clotting factor concentrates, and various people in the last 24 hours have discussed these. So modified single chain factor VIII, various forms of molecular conjugates, and then the fusion proteins. Some of these are already in the clinic, some are undergoing phase 3 studies, and some of them, like the Xten material and these pasylated materials from a Russian company called Generium, are still in preclinical analysis. But I think some of these will reach the clinic within the next 1 or 2 years. The message from this, of course, is that for factor IX, the outcomes are actually astonishing and remarkably good. Factor IX extension now is 3 to 5-fold, and so patients now can treat themselves once a week, or in some instances once every 2 weeks with an infusion, and maintain levels of factor IX which prevent bleeding. So this is a paradigm change in the way of treating haemophilia B. The situation in haemophilia A is not as dramatically good, and that's because factor VIII is dominated by von Willebrand factor. And this is a ceiling which is really basically predicted by the VWF half-life. And the only way of getting around this now is to either find a different carrier for factor VIII, which substitutes for VWF, or modifying von Willebrand factor. And companies are beginning to look at this, and we may see some of these results within the next couple of years. Now, moving on to the non-factor replacements. Johannes already discussed this molecule a little bit earlier. Most of you are familiar with this. This is the bispecific monoclonal antibody, originally described by Chugai and now being marketed and clinically trialed by Roche and Genentech. So this is emicizumab, or ACE910. It's an antibody that binds with one arm to activated factor 9 and through the other arm to factor 10. This is undergoing phase 3 studies, and those of you going to Berlin later this year will hear, I think, the results of the outcome, which have been extremely promising, I believe. And then very briefly, the rebalanced hemostasis strategies. I think there's someone here from Alnylam. So Alnylam have been working on a strategy where you balance a factor 8 or a factor 9 deficiency by knocking down antithrombin. And there are various groups that are doing this also by knocking down TFPI to rebalance the hemostatic mechanisms. The way that the Alnylam group have been doing this is using this short inhibitory RNA. This is referred to as fitusiran. This is delivered to the asialoglycoprotein receptor on hepatocytes, gets in and interferes with the translation of antithrombin message into antithrombin protein, and you end up with reduced levels of antithrombin circulating. And when those levels are reduced to somewhere in the region of 20 to 30% normal levels, you begin to see elevations of thrombin generation in hemophilia. So this is an interesting, novel, and so far quite exciting way, I think, of rebalancing the hemostatic mechanism in hemophiliacs. With that rush through, you can see, I think this is my summary of where we are with the novel alternative therapies. I think there's been extremely good initial reduction of clinical bleeding rates in these cases, including in some instances, particularly with emicizumab, of course. Some of you are probably taking part in that study, where the clinical bleeding rates have been dramatically reduced, including in some inhibitor patients as well. So the study that will be reported, I think, in Berlin will be an adult inhibitor case study using the ACE910 emicizumab antibody. The advantage, of course, of many of these therapies is that they're infrequent subcutaneous administered therapies. That's very attractive. There have been very few adverse events. Many, or some of you certainly are aware of the fact that emicizumab has had I think 4 reports of unusual thrombotic events recently reported, but my understanding is that all of those patients are now back on the antibody and very happy with their treatments. And no neutralizing antibodies have been formed to any of these other agents. There are some ACE910 antibodies, but they don't appear to interfere with PK or PD. So can factor VIII really be replaced? I think the answer may be yes. There's cautious optimism. We need to be aware of some of these SAEs, and we're waiting to see what the phase 3 studies show. So I think we'll learn much more about these within the next 1 or 2 or 3 years, and the Berlin meeting will be the beginning of the unveiling of some of this information. And honestly, I think if some of these agents turn out to be as good as they look, they will be paradigm changing for the way that we treat hemophilia. So moving on to curative strategies. And so essentially what I'm going to do is to discuss cell-based and gene-based therapies. And these are the 3 areas that I'll be discussing in the next 20 to 30 minutes. So in terms of gene transfer, I'll be talking about replacement gene transfer mechanisms. I'll end actually with some words about genome editing, because you can't give a talk without discussing CRISPR. Actually, all of our undergraduate students know more about CRISPR than they do about the DNA structure, I think, of the genome. And then some words about cell-based therapies, and I'll begin there. So this is the background slide to discuss cell-based cures for hemophilia. And I'm going to discuss autologous cell therapy and allogeneic cell therapy separately. So cell-based cures for hemophilia require cells that could be given to the patient or exist within the patient, which persists for a long period of time. There's no point in doing cell-based therapy with neutrophils or platelets, really, that are going to be there for days or weeks at most, and you'd have to repeatedly administer those. So it's obvious that you need to do this type of therapy with some form of cell or progenitor cell, which is long-lived and potentially will be differentiated in type. So let's begin with autologous stem cells or progenitor cells. So these are coming from an individual that has haemophilia. And so in this instance, if you're going to do the cellular therapy, you need to either give these cells the correct gene copy, or you need to edit the mutation present within the autologous cells. So the cells that you're manipulating don't need to have inherent 8 or 9 expression, because you're going to give them that. The good thing is, of course, is that there should be no alloimmune response, because these are autologous cells, but you will need to make space for the cells, so there will be a need for conditioning, even though they're autologous cells that are being reinfused or manipulated. So this is the type of model, and we'll revisit this again a little bit later in the presentation. But here you'd isolate, harvest autologous long-lived cells. You would deliver or edit the gene of interest. You would expand either the substituted cells or the mutation-corrected cells, and then re-administer those cells back into the autologous host. The advantages to this type of technology is then that whatever you're doing to the cells is happening outside of the body, so there's no exposure to potentially immunogenic parts of the system like vectors. That's all occurring outside of the host. And then you can also obviously precisely target the cells that you want to alter, because you've got them in front of you, and you can actually subpopulate those cells if you wanted to make sure that the cells you're manipulating are exactly the ones that you require. The disadvantage to this type of system is that this is a labor-intensive and very complex process. Having said that, with the advent of CAR T-cell manipulations, I'm assuming that in Great Britain as elsewhere, that there are now more and more facilities that are gearing up for cell-based therapies based on the back of CAR T-cell manipulations for oncology. So this is not easy, but I think increasingly this may be available at tertiary care centers because of things like CAR T-cells. You need cells that have good viability, long-term viability, and then there's the issue of conditioning. The types of cells that you might consider for this type of therapy would be HSCs, of course. Hematologists are very used to working with these cells. There are long-lived endothelial progenitor cells, and then these magic cells, mesenchymal stem cells, which, of course, if you believe the literature, can do just about anything, include produce immunosuppressive or immunomodulatory mechanisms. And here's a BOEC. We've worked with BOECs trying to do some of this work. You can isolate these from the peripheral blood, and they can be expanded to very large numbers and can be transduced with transgene constructs. So moving on to allogeneic cells. So these cells then come from other individuals. And in this instance, of course, you don't need to manipulate the genes because they're coming from normal individuals who have functional factor VIII and IX genes. So there's no substitution or editing required. However, now there's an immunologic challenge. So these cells have to be matched with the recipient. And you must use organs or cells that have inherent expression of the protein of interest. And of course, with factor IX, that's relatively easy because we've known for decades that factor IX is made in hepatocytes. And so liver transplantation and hepatocyte transplants will cure factor IX deficiency. The situation with factor VIII is quite different, and I'll allude to that again in just a moment. And again, you'll need to make space for the cells, so conditioning and some form of maybe long-term immunosuppression will be required. So the candidate cells for allogeneic recovery are listed on this slide here. So many hemophiliacs now, probably several hundred around the world, have been cured by liver transplantation. I certainly know a number who either have been 8 or 9 deficient and now no longer have haemophilia because of their liver transplants, often for coexistent HCV infection, of course. And then here's some other cells that certainly produce factor VIII, liver sinusoidal cells. Lymph node transplants can cure haemophilia A. There's a good veterinary evidence of that. I'm not aware of any patients that have been treated with node transplants, but this will cure haemophilia A. And then some people believe that bone marrow would do the same, although there's probably should be 10 question marks here because it's very contentious, I think. I'm not sure that I believe it, but there are people in the world who believe that marrow transplant could cure haemophilia. I'm not one of them. The issue of conditioning is very important. So these patients who get cellular therapies will require some form of chemoradiation strategy. This is variably toxic. Hematologists are very well aware of this. And there's also obviously problems with long-term immunosuppression for the allogeneic transplants. So this is not easy. These are complications which hemophiliacs may look at and say, this is not for me. Okay, so let's move on to gene transfer. It's not snowing at the moment, so we can move on and take some bit more time. So there's been now over 20 years of expectation that gene transfer would work for haemophilia. And I, unfortunately, have been one of the people who've repeatedly stood at podiums like this and said, this is going to work, and you ultimately lose all credibility. But thank God things are beginning to happen, as we all know. So great expectations since the early 90s. And I'm going to discuss, first of all, replacement or substitution gene transfer. So you need a delivery system for this to work. And as you're aware, there are different systems which could involve either non-viral delivery, which includes these sorts of things. So using physicochemical methods, electrical charges which can blow holes in nuclei and get DNA in. Or you can actually use brute force and ignorance and just try to hydrodynamically inject DNA. And in fact, some people do that. I wouldn't advise it, and I don't think patients are queuing up for this to happen. So what we do, of course, is we use the stealth of organisms which for millions of years have become extremely adept at getting their nucleic acid into cells, that is viruses. And one of the patients who very elegantly discussed this last night, it was a great group of, so that they basically you take a devil and you make it into an angel. I'm not sure I would go that far, but anyway, it's taking viruses which are bad and making them very efficient delivery vehicles. I'm going to talk a little bit about each one of these vector systems, but mainly about AAV, of course. So the first virus I'm going to discuss is a cold virus. So adenovirus can cause minimal human pathogenicity in most individuals. This is responsible for respiratory infections. This virus, which is a DNA containing virus, is highly efficient at getting nucleic acid into dividing and non-dividing cells. It's extremely good at getting its DNA into cells all over the body because its receptor, the Coxsackie adenoviral receptor, is pretty ubiquitous on many cell types. You can make this vector very easily, and so it was one of the lead candidates, I think, for gene transfer early on. So on the next 3 slides, I'm going to show you some results that come from our group about 15 or more years ago. So these were from some of the first studies we did in 2 dogs. These dogs have severe haemophilia A. And I'm just thinking about Nikki's studies where you're talking about lots of patients and the information you get. I'm used to working with N's of 2 to 5, and I think I still get important information. And so it's very different, the type of population, I think. So here are 2 dogs where you give an adenoviral vector expressing dog factor VIII. And the astonishing thing is here, so this scale here is, this is 500%, 10 times physiological, 20 times physiological levels. Within 12 hours, these dogs were expressing 20-fold physiological levels of factor VIII. I remember my veterinary technologist calling me 6 hours after the intravenous delivery saying, this dog doesn't have haemophilia. And it was truly a remarkable result. But you can see that by 10 days, the correction had disappeared in both of the animals. So this was a massively positive and then a massively dreadful outcome. At the same time, their ALT values rose within the first 24, 48 hours, and then by 10 days were at the level of acute hepatitis. By the way, the dogs systemically appeared fine, but they had massive levels of transaminase showing that they had acute and then sort of subacute hepatic damage. And this is their anti-canine 8 antibodies, which in one dog rose to 1,200 Bethesda units, and in the other one were also sort of around about 50 Bethesda units. So this illustrates why you do not use adenoviral vectors for haemophilia. I mean, we learned many things from this, all which were negative, but having said that, so this is because adenoviruses produces a major innate immune response. You get massively elevated pro-inflammatory cytokines, hepatotoxicity, thrombocytopenia, and in some cases, systemic inflammatory response syndrome. And many of you will remember that one of Jim Wilson's patients, Jesse Gelsinger, died when he was given an adenoviral vector for ornithine transcarbamylase deficiency. And in fact, even after we had done these dog studies, a haemophilia patient was treated with an adenoviral vector. I have no idea how that happened. It was only one patient who fortunately was fine, but certainly did not get any therapeutic benefit. So this is not appropriate for haemophilia. I have 2 slides about retroviruses. So retroviruses in the past, of course, have been the sort of oncoretroviral vectors. We're now using increasingly lentiviral vectors, which were originated by Luigi Naldini about now 15 to 20 years ago, which can get into both dividing and non-dividing cells very effectively. The original forms of retroviral vectors required cell division to efficiently get transduction, but lentiviruses can get into non-dividing cell types as well. The innate response to these vectors is minor. They integrate into the genome, which adenovirus doesn't, by the way, very stably. And the integration sites are at non-oncogenic regions. So Luigi has done lots of studies now indicating in tumor-prone animals that lentiviruses do not appear to be at increased risk of producing genotoxicity. So what's happening with lentiviral gene transfer? I don't really have time to tell you much about this, except to say that here 1 week ago, this is a 1-week-old pup who's receiving neonatal lentiviral delivery in our laboratory. So this is a collaboration with a group in Milan and Biogen. And this pup is getting lentivirus systemically. And I was thinking of Mike actually yesterday in the discussion, the patients were telling us about AD delivery or AAV delivery and how you were anxious, I think. The heart rate of a pup this size is 230 beats a minute. I was watching this and I don't know that my heart rate was 230, but it was pretty high. Anyway, there were no problems with the delivery. And actually, later today, I will learn about what the levels of factor VIII are in this individual, this pup. So lentiviral therapy is undergoing continuous interest. It's not in the clinic yet, but I think within the next 1 or 2 or 3 years, this is going to happen. So where are we now? We're using this virus, AAV. So these are the AAV particles. This is an adenoviral particle. This is used as a helper to make this virus replicate. AAV has a DNA genome which is fairly small. So one of the limitations of using AAV as a vector is that the packaging capacity has to be not much bigger than 5 kilobases. Otherwise, it's a bit like packing your suitcase at the end of a trip. You can't stuff it too full because it'll just get out of the packing case, and that doesn't work very well. So these viruses are non-pathogenic in humans. There are many serotypes due to the different capsids which contain the genome. It exists within the nucleus as extra chromosomal concatenamers. So there are circular polymers of the viral construct. And again, the innate response is minimal compared to the other viruses. Certainly way, way, way less than with adenovirus. So this is, to my knowledge, there have been no acute systemic problems with AAV delivery in all of the studies that have been done. So you can switch the capsid of AAV and deliver to different organs within the body. So here you can see that the original construct of an AAV genome, which has rep and cap sequences, which code for different proteins, in a gene transfer vector is now substituted with a clotting factor gene, a regulatory promoter element, and all that's left really are the inverted terminal repeat elements, which stabilize and package this transgene into different forms of capsids. And indeed, there are studies ongoing with most of these different serotypes which deliver to the different organs and tissues that you see listed here. So prior to 2011, there had been 8 studies carried out in haemophilia, 3 in factor 8 and 5 in factor 9. And here are the different vectors that were used in small numbers of individuals. You see there was one IV adenoviral study that I mentioned to you. But really the thing that changed all of this, I think, is the work that the group at UCL did. So here's the study that everyone's familiar with. So Amit's work published in the New England Journal in 2011. And that study was followed up by this publication in the New England Journal in 2014, in which 10 of those individuals with severe haemophilia B, so remember, and I think you all are aware of this, most of this work has been on factor 9 deficiency to this point, followed up for 3 years, and the best outcomes were persistent levels of around 4 to 6%. And the major challenge was pre-existing immunity, which produced vector-induced hepatitis, most of which was overcome with transient use of corticosteroids. Now, around this time, or actually preceding this, in Kingston, we had been working with a company which no longer exists called Avigen, and carried out studies on 9 severe haemophilia A dogs. So this is now a factor 8 gene transfer study. They were given various different serotypes of AAV carrying the factor 8 gene from dogs, and then were followed up after single infusions for a mean of 10.5 years. And you can see that we converted these dogs from severe hemophiliacs to having levels of factor 8 of around 10%. 12% was the mean value. And they essentially went from bleeding to no bleeds. So I present this information simply to say that in this small number of large animals, by the way, this is Eliza, who is a homozygous female dog with haemophilia, and she was the first large animal basically to be cured of haemophilia. And she lived for over 10 years with a cured disease. So I think the data we have to date with AAV in the large animals, and this includes studies that Tim Nichols has done at UNC for sure, is saying that single infusions of these vectors give recovery for a decade plus without the need for reinfusion of the vectors. So this is very encouraging. It's actually a little difficult to understand biologically because your hepatocytes are turning over a little, but there seems to be minimal dilution effect after this period of time. So this is, I think, very encouraging for patients entering these studies. And by the way, we've now euthanized these animals because they're old, they're 12, 13 years old, and none of them had any evidence at autopsy of any tumors and basically lived healthy lives until the end of their existence. So here are the human studies. This is the end of 2016. There are 6 studies doing factor IX gene transfer. These are the different serotypes of AAV. You can see that there are various forms being used, predominantly because of intellectual property reasons. So the different companies have used different serotypes partly to go to different organs, although really they're trying to do this all within the liver. And they're using different constructs, some codon optimized factor IXs, and then some using Padua, which I'll talk about in a moment, but I think which you know about. And then I'll come to the safe harbor method towards the end of my talk. And here are the different companies that most of which you will have heard about. And some of these individuals have representation at the back of the room here. So Padua, I think everyone's well aware of. Paolo Simeone and Vola Arruda described in the New England Journal now, back in 2009, this hyperactive form of factor IX, where if you substitute an arginine for an alanine, with alanine at this codon, you boost factor IX levels by 7-fold. So this is a gain of function missense variant which produced a DVT in a young individual in Italy, which is now being used by gene therapists to major advantage. So I think it's actually a wonderful example of the ingenuity of molecular biologists to take advantage of disease problems to make a therapeutic benefit. And that's best shown here by the data from the SPARC group. So Kathy High's company now, she's left UPenn and has now formed this company called SPARC. And these are results now which were presented at the plenary session at ASH just now a few weeks ago. And in this small group of individuals, and I think this is now up to about 6 individuals, when they use the Padua transgene, you can see that going out to, these are days post-administration, that all of these patients reproducibly are getting factor IX levels of somewhere between 25% and 35% levels, and those are now stable and persistent. So this, I think, is the best state-of-the-art evidence of factor IX gene transfer showing consistent elevation at therapeutically very useful levels of factor IX using this gain-of-function transgene. So far there's been, or there is one ongoing factor VIII gene therapy study which BioMarin are carrying out. The BioMarin folks are here today. This is using a codon-optimized factor IX transgene and AAV5 as the serotype. And I have 2 slides just showing the information. So here are the patient numbers here. Here are the weeks of follow-up. And this is information that was released last April. And suffice it to say that the majority of individuals here were treated with high-dose vector amounts. And the initial couple of patients had undetectable or very low levels of factor VIII. And 2 of the initial 3 patients did show evidence of ALT elevations. And so from that point on, all of the patients were treated prophylactically with corticosteroids to prevent the ALT increases. So also at the bottom of the slide, and John Passy presented this information initially at WHO in Orlando, a couple of the patients had very high levels of factor VIII, greater than 200% at the time of the Orlando meeting. So several of you, I think, are enrolled in this. Some of you are carrying out this study, so you know much more about this data than I do. And then finally about this study, I learned from the BioMarin folks, and thank you for telling me about this, is that they had a presentation at the JP Morgan meeting on Monday, so an investors meeting, which is summarized on this one slide. So here are factor IX levels, and these are the latest results in 7 individuals with severe haemophilia A, all of whom were treated with the high-dose vector amount. And you can see that this is the weeks after infusion, going out to 44 weeks. And here are the median and mean factor VIII levels, and at the bottom, the range. So let's just go to week 36. All 7 individuals have been followed for that period of time. The median factor VIII levels are very, very good, 99%. The mean is 115. And the range is large, but certainly everyone is therapeutic or super therapeutic. My understanding is now the 2 individuals with high factor VIIIs, one still has a factor VIII that is possibly around about 200%-ish. The other is now in the 100% region. There's still at least one individual who has a lower level, but nevertheless a level that is within a trough level that is very acceptable. So these are the first studies with factor VIII to produce therapeutically relevant levels of factor VIII. They are remarkable, extremely promising, but there are a couple of issues that I'll highlight in just one moment. And actually, here's one of the issues, I guess. So if you look at the vector doses that have been used by the studies, and if you begin with the Nathwani study back in 2011, their low-dose vector load was this, 2 × 10⁻11 vector genomes per kilo. The SPARC data is actually with a vector dose which is not much higher than the Nathwani dose. It's here, 2.5 times this. And then at the bottom you see the BioMarin data, which is pretty high, and then with the high dose it's much, much higher than they started with here. So the data with the BioMarin construct is extremely interesting and positive, but it was achieved with a very big vector dose. And remember, all those patients had to receive prophylactic steroids. My understanding is now that the steroids have all stopped and the patients have no evidence of transaminase elevations. So I think that was a transient requirement, but all the patients have done well after several weeks of corticosteroid therapy. The other issue, I guess, before I forget, is I think the other question about the BioMarin data is the variability. I showed you the SPARC data with all of the patients, albeit in about 4 or 6 patients having fairly predictable factor IX levels. The BioMarin data goes from 10% to 200%. It's all therapeutic, but it would be kind of nice if there were a little bit more equality and predictability. Here are the potential gene therapy complications. One of them is hepatotoxicity. This usually occurs around 1 month to 3 months. It responds to steroids almost always, and it's likely in most instances due to the generation of cytotoxic T cells which see AAV capsid that's being presented on the surface of the transduced hepatocytes. And so we recognize this, there are ways of treating it, and it looks as though it's overcomable. And then the other question is about long-term genotoxicity. And please, I do not want you to go away from this talk, because I've given this once before and all people remembered was this word. I do not want you to think that this is causing liver cancer. There have been questions from a mouse study that was carried out about 10 years ago that liver cancer was associated with AAV gene transfer. I think that's probably entirely wrong. And wild-type AAV sequences have been found in pieces in liver cancers. That is very different to AAV vectors. So again, there are multiple question marks here. Do not take away a message that AAV vectors cause liver cancer. However, AAV sequences do insert into the genome because you give trillions of particles of AAV vectors. And so if you look at this study, so here around here is the different chromosomes, and in the black bars you see insertion sites in 3 humans who had liver biopsies 1 year after getting AAV vectors, and there were 134 unique insertion sites which were random, and none of those insertions appeared at oncogenic locations. So you have to say, because of the trillions of vector particles, that some of those will get inserted into the genome for the lifetime of an individual, but the likelihood of these being oncogenic is extraordinarily small. The other lines here are on a bunch of non-human primates, just illustrating in 3 different tissues that, again, there are insertion sites. Okay, so the summary of the current status of hemophilia gene therapy is, I think, that factor IX therapy is proven to be effective. The magnitude of response has been relatively unpredictable until the SPARC study, which looks very predictable and very encouraging. For factor VIII, it's now been proven to be successful in 1 study, but the vector doses were high and the levels were variable, but all therapeutically very positive. Genotoxicity risks are very low, and the host immunity is the major safety issue. It's not predictable, but steroids work in preventing it or treating it. So I'm now just going to say very briefly a word about one gene editing thing, and then I'm going to finish. So I think everyone's very well aware that there's a lot of interest now in ways of editing the genome, and there are 3 systems that are being used. The 2 systems shown here, TALENs and zinc finger nucleases, use protein motifs, either these transcriptional activator-like motifs, which guide a nuclease to a site in the genome, or you use zinc finger protein motifs here and here to guide an enzyme to cut the DNA at a particular region, as shown here. And you heal the double-stranded break through either homologous recombination, which requires the delivery of a template, or through non-homologous end joining, which is error-prone because you'll get insertions and deletions when you heal the double-strand break. And then finally, that everyone knows, probably people on the street have heard what CRISPR is. I mean, it's just astonishing how this is now known by many, many people. So this is a technology which is going to win people Nobel Prizes. I think there's no doubt this will be Nobel laureate worthy, where you use now a guide RNA to deliver an endonuclease, usually Cas9, to a target sequence in the genome. And this is much easier to do because the guide RNAs to develop and screen are a lot easier and cheaper than the previously alluded to TALEN and zinc finger nuclease methodologies. So I'm going to show you 3 slides on this study, and then I'm going to finish. So you can use engineered nucleases to guide genes to safe harbors in the genome. And this is a study that some of you are probably aware of from the group at Sangamo, where they used zinc finger nucleases, so in this case not CRISPR, to guide the insertion in the first intron of the albumin gene, the cDNA for factor IX. So essentially they're guiding this region, which encodes for factor IX, into the albumin first intron, which is a safe harbor, and at the same time uses now the albumin regulatory sequence, which is out here, to drive expression of a chimeric transcript of part of albumin, the first exon, and the clotting factor cDNA and protein. So this is a very elegant method of inserting a gene in a safe place, But not only is it safe, it's transcriptionally very effective because you're using a very strong liver element, the albumin promoter, to drive expression of a clotting factor transgene. And this is the type of results that they published in their Blood article. So here is the results with their mouse albumin targeted zinc finger nuclease. And you can see that these levels, this is weeks after delivery, are 50% and higher of the human factor IX levels with this delivery. So for time purposes, I'm actually going to tell you that CRISPR has been used to change, actually alter and fix factor VIII inversion events. But CRISPR is a long way from the clinic. Inevitably, it will reach the clinic through methods like this, taking cells out of the body, using gene correction with something like CRISPR, reinserting these cells back into the individual. But realistically, this is not going to happen, I think, for at least, who knows, 5 or 10 years. So these are the final conclusions. What I would say then is that it's pretty clear from this meeting and maybe from my presentation that the current range and potential of haemophilia innovation is remarkable. I mean, this is really a fire hydrant of information and therapeutic benefit for our patients. I think that haemophilia will increasingly be treated with strategies other than standard clotting factor concentrates in the next 5 to 10 years. And some of the things that I've alluded to will be truly massively changing and disruptive for haemophilia therapies. So curative approaches are already undergoing clinical trial evaluation. We heard from 2 of the patients yesterday who told us about how positive they are about these treatments. And these treatments will inevitably be used more frequently in the future. And then probably really importantly for this audience, where there's the next generation of treaters, it's critical that haemophilia treaters are knowledgeable about these innovations to optimally individualize future therapies. And so with that, thanks very much indeed for your attention, and I'm happy to take any questions.